Hey, hello guys, welcome, Manakam, Vandanam, Namaskaram. Today we are going to see magnetism and matter. Well, today my pronunciation and as well as maybe my enthusiasm can be a little bit less because it's morning 6:30 and I don't know how's my hair is. Okay. I don't talk during morning. I don't like to talk during morning, but I'm taking this video since I have an examination. So please excuse me. Okay, so we shall get started with it. What we are going to read in this lesson is actually this is a very underrated topic. This is a very underrated chapter. Even in the last NEET examination of 2025, they didn't ask any questions. Yeah, there wasn't even a single question that was asked from this chapter. There are totally two different chapters that are highly underrated in entire 12th. Then in 11th also there are 2 to 3 chapters which are underrated. But 11th and 12th very important for NEET examination. That everyone knows now. But why am I saying this? Because slightly I'm sleepy. Okay. So we are going to discuss about, first we will talk about magnet. Okay. See, magnet is a substance which can attract or repel. It has the ability to attract or repel, and also it is like, what else? That's it. It is able to then it also has, we all know that magnet has two different poles, right? So it has two different poles. Okay, so namely what are those? They are actually north pole, then the south pole. South pole is actually negative, south pole is actually negative, and north pole is actually positive. Many of us would have guessed it wrongly that south pole is positive, north pole is negative, but it is actually vice versa. North pole is positive and south pole is negative. Then monopoles does not exist. Very important point. This can be asked as 1 mark. What is monopoles? See, when you are having a magnet, okay, now you are cutting it. Okay, for an example, I'm just going to cut it here. Okay, over here. If I cut it over here, then you will be having two different parts of this magnet, two different chops of this magnet. One will be this, then another will be this. Okay. Here, this magnet will have its north pole. This magnet will have its north pole and south pole, as well as the small magnetic clip will also have its north pole and then south pole. Okay, it will also have its north pole and then its south pole. So this is what this point is. Monopoles. What does monopole mean? Mono means single. Pole means a particular sign you can take or a particular character. See here, this is a pole, this is a pole. In case of dielectric dipole moment, okay, in case of dipole moment, you can see that here you will be having a positive charge, then a negative charge. Here this is a monopole and then this is a monopole, and here monopoles exist. That means positive charge can exist separately and negative charge can exist separately. But here it is not like that. North pole will never exist separately and also south pole will never exist separately. They will be together. Always they will be together. Like if a problem comes to the north pole, then south pole will come and help. If a problem comes to the south pole, then north pole will come and help. Like they both are very thick friends. Then this is some basics. Okay. Next is magnetic length. See, magnetic length is actually different and length of the magnet is different. Well, these terms can appear to be similar or to be the same thing, but it's not. See, you just take a magnet, okay, you just take a magnet. In this magnet, the total geometric length, that is the length that you are measuring by using a scale, okay, by using a scale you will be measuring, right? This length is what called as length of the magnet or geometrical length, or this is also okay to be said as the geometrical length, that you are using a scale and then you are measuring it. That is what we will be calling it as this. But whereas coming to the magnetic length, it is not length of the magnet, but it is a part of length of the magnet, the major part of length of the magnet. It is, you can also say like this, that is the effective part. Like we cannot give guarantee that each and every part in this magnet is being used to give the magnetic field. So the parts which give the magnetic field or which produces the magnetic field effectively is what the magnetic length, that length of that part is what we will be saying it as magnetic length. So that has a formula, we will check about that also. Okay, so here this is actually just L, okay, this is actually L, they will be giving it as L only, so we can also call it as geometrical length. Okay, geometrical length, which is L. Okay, so here it does not have any separate formula, but here it has. Here it is actually equal to 5 by 6 of L. That is a part of L. This is a fraction, and in this fraction is actually lesser than 0. Okay, sorry, lesser than 1. This fraction is lesser than 1. So absolutely this total value is going to decrease. So from this also we can say that, okay, from this we can say this magnetic length is actually lesser than geometrical length. Okay, is actually lesser than geometrical length. And magnetic length, length of the magnet is actually 2L. Okay, like you are having a magnet. Okay, it depends. Okay, in the question, sometimes they could have given you the entire length. Okay, this is for a north pole and south pole. Just this length is 1L, then this length is another L. Okay. Okay, so the entire length is going to be 2L. So that is why the length of the magnet is over here as 2L, but in the question they could have given you the entire 2L itself, or they could have given you just the L portion. So that is the place where we all have to be very strong. Okay. Just like electric dipole. Okay, so this is here. Then pole strength. Okay, then pole strength. Okay, so what is pole strength? Okay, so just by using a name even we can very easily say what is pole strength. This is north, this is south. So this is a pole, then this is a pole. So strength of this pole against strength of this pole. That is what we'll be calling it as pole strength. Okay. So this is actually represented by small m. This is actually represented by small m. And then a formula for this can be given as q into v, velocity into charge. Okay, this is actually a relationship between q and v. So that is what pole strength, the strength of the pole, that we can say it like that also. Then coming to the definition, the ability the ability of a pole which can attract or repel the atoms. Okay, so that's it. Then coming to magnetic momentum. Not momentum, sorry. Okay, so what is magnetic moment? It is like, you can take it as the entire strength, okay, the entire strength of this magnet. That is what we'll be calling it as magnetic momentum. Okay, so that means what? This means that you are going to see, in case of electric dipole, what were you taking? You were taking Q into, okay, Q into then that length, okay, that length, that is 2a you can take. Okay, so this is what you will be taking, no, P na. But here P is what equal to Q into 2a. Okay, here you are going to take like that only, instead of Q, here it is capital M, it is represented by capital M. Okay, here it is capital M. Capital M is equal to small m, that is this pole strength, into 2L. Okay, into 2L, that is the entire length. Okay, that is the geometrical length. Okay, then coming to its SI units, your SI units are going to be, see, what is this? Okay, what is this? This is just pole strength, right? Okay, and then what is this? This is just your length. So you can take it as ampere meter square. Okay, ampere meter square. Then, as I said, this pole strength, okay, this pole strength, north pole is positive, then your south pole is negative. Okay, so this is M, then this is also M. Okay, so some concepts, okay, some theories. We will just see some theories. Okay, so the first theory is that Earth acts as a magnet. I'm very hungry now. Okay, Earth acts as a magnet. See, okay, so north, south, okay, the, like Antarctica is a pole, then also we can take the Greenland side, that is also a pole, so these two are poles, and here magnetic fields will be there. By the way, this is a very weak magnet, not such a strong magnet. When you are comparing its size and in the magnetic field it produces, okay, and also there will be even they are saying that even there will be current, not current. Okay, so there will be a change in the magnetic field even when an aeroplane flies. But the thing is, you cannot produce current because it is very less in amount. Okay, the current that is being produced because of change in magnetic field is actually very less. Okay, because of this weak magnetic fields. These fields are very weak. Okay, so this is for Earth. Then another thing. This is the thing that is used to make a compass. Okay, they found this, then they made compass. Okay, to make compass, what they did is they had see, when you just suspend or when you just make a magnet to fly without any force, external force on it, it is impossible. But okay, when you suspend it by using a thread, okay, then it will be pointing towards north and south. Okay, north and south. South will be pointing towards north and north will be pointing towards south. They are actually attracting each other, no? Okay, they point towards north and south. That is the thing. Then very simple thing, that is what we have been reading from our younger ages, that is north versus north will repel, then south versus south will repel, then north versus south will attract. So these two cases, attraction is there, okay, here sorry here repulsion is there, is there, then here attraction is there. Okay, then as I said that here monopoles does not exist, that is also a theory, or that is also a point. Then magnetic field lines, okay, very super concept, magnetic field lines. Okay, see, this can be asked in your 2 marks. Also in board examination. Okay, now we just check here. Okay, so they will be forming closed loops. Closed loops, like continuous closed concentric loops. Okay, okay, then so these are actually circular loops. If you want to know the image, it's very simple. Okay, when a current is being produced, this is how, okay, magnetic field will be there. Then solenoid, and for bar magnet I will say. Okay, so for solenoid, okay, then coming to here, okay, wait, here magnet, solenoid, okay, and electric dipole. Okay, see, first I will give you this one, that is number of magnetic field lines is directly proportional to, okay, is directly proportional to strength of the, or concentration of the magnet. Okay, the magnet's concentration, that is magnetic momentum's concentration or magnetic field, okay, will be very high if the number of magnetic field lines are high. Okay, see, this is what your magnet is. So here you are having north, here you are having south. So here this is going to be positive, then this is going to be negative. So always we all know that from positive to negative it will be going. So like this. And here also like this only. Then here also. Okay, like this only it will be going, but inside alone it will be opposite. Okay, it will be from negative to positive. Okay, but here outside it will be positive to negative, here it will be negative to positive, but mostly it will be from even here we have read what, here also we have read that it will be from from negative to positive. Yeah, we have read that it is from negative to positive. Sorry, here we have read that it is from positive to negative. Okay, because negative charge like this. Okay, then positive charge is like this. So they will all go here. Okay, this is what your for your magnet you can say like this. This is actually very similar with the EMF. You know, EMF is actually having one direction. Actually, EMF and current are having opposite directions in the circuit, and EMF and the current are having the same direction inside the battery. Okay, with the conventional current we are talking about. When you are taking the conventional current, this is what the case is. Now coming to solenoid or bar magnet. Actually, this is also a cross section, and this cross section that I am about to give is also you can be used for bar magnet. Okay. Well, first you can draw this when they are asking for magnet, you can draw this and then this. Okay, both can be drawn. But yeah, as I said that, so draw both of these or draw just this. Okay, but don't not draw just this. Okay, because this is a diagram that we have read in 10th standard. Now what I'm going to give is something that we are reading now. Okay, so you will have to intersect like this. Okay, so that means just a center line, and I'm drawing very good lines. Okay, a center line with this direction. See, okay, this direction, the center line. Then here. And here. Okay, see here, these two directions are those same. Oh god, my English is very terrible, as I said. This direction and then this direction, the direction of these two paired magnetic field lines are the same thing. Okay, are in the same direction. As I'm sleepy, I cannot even think. Okay, but here you will be having a loop like this, and here also you will be having a loop like this. Okay, but the thing that to be noted is, here you will be having the same direction as here, that is like this. Okay, but here you will be having the opposite direction. Like when you are taking this side, it is same direction. When you are taking this side, it is like opposite direction. When you are taking this side, opposite direction. When you are taking this side, it is the same direction. So it's the particular part which you are taking. Okay. Next is the electric dipole. Very easy diagram that we have already read it. Okay, so it's your wish. You can assume this to be positive, this to be negative, or you can assume this to be negative and then this to be positive. Same thing. You can assume this to be south and this to be north, or the vice versa. Okay, it's your wish. So I will assume this to be positive, then this to be negative, then okay. So it will be going like this. See, so this is what your diagram is. Okay, so so this is how your diagram will be, and then you can draw this thing. Now we shall all enter into our formulas, a very important time. Like till now we were talking. Here also I'm going to talk. But now we are going to check with some formulas. Okay. The first formula is actually with some applications that I've brought. Okay. So for an example, you are having a magnet. Okay, so this is your magnet. Okay, this is your north and south pole. North and then south. Then, since we all like to torture everything, so we are going to torture this magnet, and then we have bent this magnet like this. Then see, now this will be having a new magnetic momentum. Okay, here this is having a magnetic moment, and this is having a magnetic moment. This magnetic moment already we have seen. Okay, already I have said here. Okay, but here now this is going to possess a different magnetic moment. That new magnetic moment is none other than m dash. Okay, m dash. Let this be m itself. So here if this is m dash, then it is 2m sine theta by 2 by theta. Well, what is this theta? This theta is like this angle. Okay, this angle. How much you have bent it? Okay, so how much you have bent it? That's what this theta is. Okay, so and also see this. Now you are actually adding two magnets. You are having a magnet. Then to this magnet, you are actually also adding another magnet. North, south. Okay, so you have done like this. Then this entire total thing will have a different magnetic field. That thing is what you are. Okay, see, magnetic field is what? It is actually a vector quantity. Okay, so magnetic field is vector quantity, correct? So m is equal to, you all know how to add this vector and this vector quantity. Okay, so this one, let it be m1 and let it be m2. Then this thing is going to be, okay, so m net, okay, is root over m1 square plus m2 square plus 2m1 into m2 cos theta. But here theta is what? Here you can very easily see. That here it is 90 degrees. Okay, here it is perpendicular. So that means cos 90 is 0. So we will just neglect this term. Okay, so it's just like this when it is exactly 90 degrees. But whenever you are bending this with some theta, okay, okay, so like this, north, south. See, it need not to be always here south, here north. Here it can be south, here it can be north. But make sure that these two are opposite, because when they are same, it will be like repulsion will be there now. So that is why. Okay, so you are having like this. So here it is actually of this entire angle, this from here to here, okay, here to here, wait a second. Okay, so this angle is there. This entire thing is pi, that is 190 degrees. This we all know. Now, this entire thing is actually going to be theta. Then what is this going to be? This is going to be pi minus theta. So you are supposed to take this angle. This angle only you are supposed to take. Do not take this angle, the angle between two magnets. That's not correct. You are supposed to take the angle between like this. Okay. So here you are going to see. Let it be m1, let it be m2, then your values m1, then m2, then m net is equal to root over m1 square, m2 square plus 2 m1 m2 cos pi minus theta. Okay, so cos pi minus theta. Okay, so that is there. Okay, this is the way like how much you can torture magnets and how like you can align them. Next is magnetic field at a point caused by a solenoid or a bar magnet. Okay, so I don't know whether do I remember that derivation or not. Let's see. But I know the formula. Actually, I don't know whether did I say that or whether did I take seminar about that. But in one of the videos, I should have said about like a bar magnet is equal to a coil. Okay, I have that written, so maybe I would have. So we all know this one formula, that is because of a circular ring. Okay, so mu naught by 4 pi into 2, sorry, into I r square by, okay, so this is what the radius is. Okay, this is also radius. This is the distance from the point. Okay, this is what the point, this is what that x. Okay, this is what a, and in this one you can take it as, you always wait, why to confuse everything. We will keep, okay, we will keep this as x, we will keep this as r, we will keep this as a. Okay, this we will be keeping it as r, we will keep this as a, we will keep this as x. Okay, so then that means this formula will be changed. So What is A? A is the distance from the center to the particular point which you are checking, like how much is the magnetic field. Okay, so this is what your magnetic field formula. Wait, I have not yet completed. By a magnet, so we have to somehow get here magnetic momentum. Okay, so how will we get here magnetic momentum? How can we relate two different concepts? Oh god, it's 7th and all three. Bb is equal to mu naught by 4 pi. Okay, mu naught by 4 pi into, see here this radius, okay, this r is going to be very negligible. Okay, it is very negligible. Why is it negligible? Here it is negligible because here r square anima should come. Okay, see the size of a magnet itself is already small, and then in this if you are coiling it, then it is going to be still more small, right? So that is why this is going to be very negligible. What does the word very negligible mean? So I by here r square, then here 2, 0 plus a square to the whole power of 3 by 2. Okay, so here you can write it as a cube. Okay, here we can write it as a cube. So till now what I have done is correct only. Now what you are going to do is, now you are going to multiply. Okay, now just multiply and divide it by pi. Okay, here then you will be getting B is equal to mu naught by 4 pi into, see here it is pi r square. So what is pi r square? R is the radius fortunately, so you will be getting it as A. So here it is IA. Okay, IA square. So just see, what am I saying? Okay, next here we will be getting 2 pi A cube. Okay, so 2 pi A cube. But here how, wait, here how come? Here it is supposed to be, no, here it is just supposed to be 2, no? Mu naught, that's it. Okay, that's it. So this is just 2 pi. Here it is not supposed to be. So now we have got it like this. We have all got like this. Then IA, see remember this, IA is equal to capital M. And also QV2L is also equal to capital M. Okay, so these two are important formulas. So which is equal to B, so mu naught M by 2 pi A cube, where A is the distance. See, A is the distance. Okay, and also you can multiply here 2 and here divided by 2. But why are you doing this? Is also a correct formula only, but the standardized formula is here to be 4 and here to be 2. You can multiply and divide by 2, but it's okay, not a problem. Okay, so this is a derivation. Now then after this we are going to compare, like from here to all the major formulas. Okay, so we are also having some definitions, but other than the definitions we are having lots of formulas. So from here to all the formulas, it is, okay, so here it is already we have seen. Okay, we are going to change a few things that are, okay, that is, those things are going to be, you will be substituting 1 by epsilon naught with mu naught. Okay, see here it is in denominator, here it is in numerator. That is something to be noted. Okay, then you will be substituting Q by, E by, okay, electric field by magnetic field. Then you will be substituting P, okay, dipole moment by magnetic momentum. That's it. Okay, dipole moment by magnetic momentum. Then also Q by M. Okay, so Q by M. So So here we shall start the substitution. So first of all, torque is equal to mb sine theta. Sorry. First, we shall start from our electric. Okay, our electric thing. So wait a second. You are having magnetic field lines. Which is theta. So here you are having it as to be magnetic B. Okay, so torque. Oh god, this side only. Correct. Torque is equal to mb sine theta. Over there, what did we have? Okay, over there we had Pe sine theta, isn't it, for torque? Then we had also minus Pe cos theta for the work done or for the energy. Okay, so you are having it like this. Now you are actually finding. Now we have to find the work done. Okay, so to find work done, it is very simple. See, torque is equal to, well, what is here? The distance. Torque is equal to torque into d theta. So here d torque, here also, like, you will have to integrate, here also you will have to integrate. Then while integrating, wait a second, here it is dw. See, you are actually integrating. You have to find the work done. The formula for work done for this tiltation is actually, okay, 15. So the formula for this work done is T is equal to mb sine theta. This is for torque. Then you have to find for work done. So work done is what? You are actually tilting it from one angle to another angle. So you can keep it as theta 1, then theta 2. Okay, so work done is actually just the integrated form, just work done itself. Here you have to check. Okay, so what is torque? Your torque is going to be mb sine theta. mb sine theta into d theta. Okay, then you are having here as theta 1, then theta 2. Okay, so you can take the constants out. Okay, so mb theta 1, then theta 2 sine theta into d theta. So what is the integration of sine theta and then d theta? The integration of sine theta d theta is going to be cos of theta to upper limit minus lower limit. Okay, upper limit minus lower limit, but actually you are changing it from this angle to this angle, right? So So 1, 2, 1, 2, 1, 2. So upper limit minus lower limit. This is your work done. And then, by the way, the equilibrium position is there, and then unstable position is there. Like equilibrium itself is having of two different types. That is going to be stable equilibrium, then the unstable equilibrium. Okay, see, so always remember stable equilibrium will be very less. That is the minimum value. So where will be cos theta minus 1? Okay, so you will be having, oh, it is not right thing. Minus mb. Okay, so 180 degrees. No, theta degrees is equal to minus np. Okay, so cos 0 degrees is going to be 180 degrees. Okay, so 180 degrees. Here it is very minimum. Then theta, where will be plus 1, 0 degrees. Okay, so 0 degrees. Okay, so torque is equal to PE sin theta. Then here what will it be? Work done is equal to minus PE cos theta. Then here what will it be? Then we have energy. Energy is what work done. Okay, so then axial. So at axial point we are having EA is equal to 1 by 4 pi epsilon naught into, okay, this is what, this is axis now. So axial, it will be 2p by r cube. Okay, then we are also having equatorial point. Okay, here you have to put minus. Okay, 1 by 4 pi epsilon naught into, okay, see here it will be just p by r cube. Then magnetic flux. Okay, first we will write for here. See, what did I say? First P should be changed with capital M, then E with B, then sin theta B, sin theta itself. Okay, then work done. Work done is equal to minus, same thing only. So MP cos theta. Then here EA is equal to 1 by 4 pi. Epsilon naught should be changed into what? Into mu naught. Nah. Mu naught by 4 pi. Okay, into 2m by r cube. Okay, then here EQ is equal to minus 1 by 4 pi into, here it should be mu naught. Okay, into m by r cube. Okay, see what formula did we prove here? What formula did we prove here? See, this 1 by 2 pi, the same thing only. This formula only we had proven there. Okay, then magnetic flux. In this magnetic flux, you know, you will be reading in a lot of places. So you just read it in one place, then use it in different places. Okay, so flux is equal to magnetic field into A. All these are vectors. So to remove this vector quantity, okay, so flux is equal to BA cos theta. This BA cos theta, BA cos theta, BA cos theta, here and there you will be using in EMI, electromagnetic induction, correct? So you will be using this in everywhere. Okay, in EMI. Okay, you will be substituting E is equal to in place of minus d phi by dt. So lot of places you will be using. So this is important. Okay, so what is magnetic flux? It is the number of magnetic field lines that has crossed per unit area is what known as flux. Okay, not only this flux, see any flux you can write it as that quantity. Like for an example, electric flux in sense, then you can write it as electric field into the area that it has crossed. Okay, that is what that flux should be having, its area. Okay, then here any flux, here it is magnetic flux now, then here magnetic field, here it is electric flux now, then here also there is electric field. Okay, so this is something. Then by the way, the SI unit of magnetic field is going to be Tesla. Okay, then its CGS unit is going to be Gauss. Then see, 1 Tesla is equal to 10 to the power of 4 Gauss. Coming to the SI unit of this one is going to be Weber per meter square. Okay, so yeah, Tesla per meter square. Sorry, it is just Weber. Okay, Tesla per meter square or Weber. Weber. Then Gauss, Gauss law for magnetism. See the surface. Okay, so in this surface, the total net magnetic field that is there is actually going to be 0. Okay, so that is going to be 0. Okay, so the total thing, so that means summation of all the magnetic field is going to be 0, and also this is a formula. Okay, B into dl is also going to be 0. Can you all remember the same thing only we have written over Ampere circuit law? In Ampere circuit law, like the very similar thing. That is what even we are writing over here. So see, whenever you are calculating the integration in a fixed place, okay, see in this spot you are calculating the integration, then this is a closed spot, right? So you will have to put a round like this. That's very important. Okay, if you don't put none, then that is wrong. That's not correct. Okay, so the sum of the magnetic field enters is equal to sum of the magnetic field that leaves. Okay, so then cutting of a magnet. Okay, then cutting of a magnet. See, this is a magnet. Okay, so my leg has started to pain. I don't know why, but it's paining from the morning before taking video itself. So we shall stop it from here, and we all can meet in a different video. So that's it for today's video. We will be meeting in another amazing video. Till then, bye bye.